An estimator is a rule, a formula applied to the random sample for estimating a population parameter. The distinction on this page runs through the whole course. The sample mean as a formula is a random variable. Draw a different sample, get a different value. The number it produces from your data is the estimate. The estimator varies across samples. The estimate is fixed once the data are in hand. Imagine drawing sample after sample and computing the mean each time. The distribution of those values is the sampling distribution of the sample mean. Because the estimator is a function of random data, it is itself a random variable, and its spread tells us how much an estimate would vary from sample to sample. That spread is the basis for all of statistical inference. First property, the sample mean is unbiased. The derivation on the page takes 3 steps, each worth naming. Linearity lets the expectation pass through the constant 1 over n. The expectation of a sum is the sum of expectations. And random sampling means every observation has expected value equal to the population mean. String them together, and the expected value of the sample mean is exactly the population mean. Unbiasedness in general says the estimator equals the parameter on average over repeated samples. The sample mean is unbiased for the population mean. Least squares will be unbiased under the standard assumptions of Chapter 5. One subtlety deserves emphasis. Unbiasedness holds at every sample size, small or large. It is a statement about the average, not about any single draw. Second property, the variance of the sample mean is the population variance divided by n. Independence lets the variance pass through the sum, and the algebra collapses to sigma squared over n. Read what that means. With 100 observations, the estimator's variance is 1/100th of the population variance. With 10,000, 1/10,000. More data, less uncertainty, at a precisely quantified rate. In practice, the population variance is unknown, so we substitute the sample variance, giving the estimated variance of the mean and its square root, the standard error. Memorize its role. The standard error measures the typical sampling variability of the mean. It shrinks like 1 over the square root of n, and it is the building block for every test statistic and confidence interval to come. Here at last is the promised answer from Chapter 2. Why divide by n minus 1? Because the squared deviations are measured around the sample mean, which was itself computed from the same data. One observation's worth of information is used up, a lost degree of freedom. Dividing by n gives a biased estimator. Dividing by n minus 1 restores unbiasedness. The two-observation illustration makes it stark. The two deviations are mirror images, only one is unique. Consistency is the large sample property. The estimator converges in probability to the true parameter as n grows. The sample mean is consistent for a simple pair of reasons. It is unbiased, and its variance, sigma squared over n, shrinks to 0. With enough data, it lands arbitrarily close to the truth. For complex estimators like least squares, consistency is often easier to establish than unbiasedness, which is why it becomes the workhorse property later. Keep the two properties distinct. Unbiased means on average correct at every sample size. Consistent means increasingly accurate as the sample grows. An estimator can be both, like the sample mean. It can be biased yet consistent, like the maximum likelihood variance that divides by n. Its small bias vanishes as n grows. And it can be biased and inconsistent, which is the one combination with nothing to recommend it.